I think it's recording. I did this with algebra. No, I don't teach algebra. Geometry. And I did the whole thing and there was no volume. So Anthony tried to watch the video that was all volume with the blue funny picture last time, right? So I got to get it right somehow. So we're just going to, persistence is the name of the game. All right. Hey, do you have these notes out in front of you? Everyone does? Check in with your group. Ask them, do you have the notes? Do you have the notes? Do you have the notes? Okay. So here's what we need to be able to do. We need to be able to understand the difference between the tangent and the slope of the tangent line. So the tangent is going to be that line that touches the graph exactly once. The slope of the tangent line is the actual derivative. And it's important to keep those two things different. So when I pick a point like x is equal to 0 and I go to draw my tangent line, that tangent line is a linear equation. That's my tangent. What I care about is estimating the slope. So if I look at how much this rises and runs and rises and runs, I'm going to say it's about, did you say positive 1/2? It's definitely less than 1, right? If I look at the slope of the tangent line at negative 1.3, we'll put that around here. So that one was pretty close to 0. At an x value of negative 2, when I estimate that tangent line, when I look at the slope, I'm going to go back to a slope of about, it looks like negative 2. At a slope value, or at an input value of 2, that looks more about like 1. So when we're looking at the graph of the function, sketching the derivative, it starts by sketching the tangent line, and it finishes it by me estimating the slope of that tangent line. Resumed. Good news. All right. When we come down here, use the graph of the function to sketch the derivative at each of these points. So here's an interesting conversation that we had. When we looked at a lot of these points, x is equal to 3 was not a problem because there's my derivative, which is going to be about 0, I'm guessing. Negative 3 was not a problem. That looks like some positive number. When I get to negative 4, I've got a problem. And when I'm at positive 5, I've got a problem. And the reason our problem exists is because of this sharp point here and then this jump there. So we need to talk about two different conversations. One about whether or not a function is continuous and whether or not it's differentiable. So the derivative, or the slope of the tangent line, exists for each point in the domain except, and we want to make sure we understand this is a conversation about except, any place where it's discontinuous. So if I have a hole or if I have a jump, I cannot take the derivative. It's not differentiable. If I have a sharp point, or what we call a cusp, or even something that looks like this sharp point, this cusp, I can't find the derivative of it. And if you want to know why, when you see me estimating with my sweet little ruler here, when I go to find it where it hits it once, I've got a bunch of choices because it's a point that sticks up. So when you want me to find the slope of the tangent line, you want to be like, which one? So we can't find one tangent point because this graph has a bunch of different times that I can draw the tangent at that one point. So a vertical tangent line, if you have a slope, or if you have a function that has this kind of noise happening, when we go to find the tangent line, we end up, and I should have drawn this a little bit more vertical if I was able to erase, if I wasn't so old school. When I start looking at this, if I go to draw the tangent line and it's vertical, remember that the slope of a vertical line is going to be undefined. So the interesting conversation is we can have functions, and within those functions, some of those functions are continuous. And within those continuous functions, some are differentiable. Everything that is differentiable is continuous. Everything that is continuous is a function. But some functions are not continuous, and some continuous functions I cannot take the derivative of. And this sharp turn or corner is what tells the difference between those continuous functions that can and cannot be differentiated. Are we okay with that? Okay. So on the back of this worksheet, we had this conversation where you were to go ahead and talk about which x values. And I think it's great. I love this box where we talk about not continuous and not differentiable. So would you please talk to your group mates about what you filled in for these two boxes and these two boxes for this graph? And your markers that go. Alright, so do we agree? For the first graph, at x is equal to -3, we have a hole. At x is equal to 4, we have a jump. What?
Do we have to write why we put it in?
I would, just because it's your notes and you want to make sure that you understand why. On a quiz or a test, if I ask you to justify, that's what I'm looking for. Okay? So it's kind of good practice to make sure you understand, but you won't get graded on it, Adrian, unless I say justify. Okay? Yeah. What would you like?
I was going to say, can we put the -3 and 4 in the other box too?
Right. So at -3 and 4, you can't differentiate it because it's not continuous. But it's nice to be able to tell the difference between these two. Don't prevent it from being continuous. They just prevent it from being differentiable. Does that make sense?
So if we put like those like in the previous box,
If you put these in this box, you'd be wrong. If you put these in these box, you are right. But if I ask you about continuity, I want you to be able to tell the difference. So if you listed -3 and 4 in here, you're still right. You're fine. But what I want you to be able to tell me is the difference between which causes which problem. Does that make sense, Kaylee? Okay. All right. Here, not continuous. At -5, I have a hole. At 2, I have a jump. At -3, I have, I don't know, do you like the word sharp, point, corner, or cusp? I picked cusp because it's less words, or less letters. But whatever makes sense to you, whether you like it as a corner, a sharp corner. So that's the conversation about continuity. Would you please look at the front and the back and talk to your group mates about what is the thing you think is the trickiest on your mark, set, go. Okay. So your second note page was where we discovered what the power rule was. And I divided you up into groups, and each of the groups did the limit definition of the derivative for each new power of x to the first, second, third, and fourth power. And if you recall, I did x to the fourth power, and it filled that entire board. X to the third took a lot of space, x to the second, not quite as much, and x here. And our goal was to figure out a pattern that we found. And what you ended up realizing for each of these is when you took the exponent and you brought it to the front, and then you took x to the 1 less power, you were able to shortcut that whole limit definition of the derivative. So finding the derivative of x squared, instead of taking the limit as h approaches 0 of x plus h squared minus x squared all over h, doing all of this and recognizing that you're going to get your highest level terms that are always going to be a zero pair and cancel out. You're always going to be able to factor out an h. And then what you're going to be left with is an expression to 1 less degree. Instead, what we figured out was we can take this power and stick it in front of 1 less power of x. We can take this power and stick it in front and have 1 less power of x. We can take the power, stick it in front, and have 1 less power of x. So the joy in this lesson is recognizing that even though you understood this, and you can do that work with no problem, and if on the quiz someone says, use the limit definition of the derivative, I need you to go back and plug it in and show me that it works. Moving onward, we've got some pretty cool shortcut rules that we're going to start embracing fully, because it's going to save us a ton of work. So at the end of the day, whatever power is on n, if I have a function, the derivative of that function is n in front to 1 less power. So the derivative of a cubic function is always quadratic. The derivative of a quadratic function is always linear. The derivative of a linear function is always constant. And then we can understand the derivative of a constant is always going to be 0. So was this important conversation. Did you notice the pattern? Yes, we did. There it was. And we are going to, from now on, call this the power rule. So then we wanted you to practice on the back. And Anthony, boy, did you miss a crazy class because my technology was so poorly behaved. I don't even remember. How far did we get? Did we get through each of these examples?
Yeah.
I was in such a frazzled state. So here's the scoop. When you see a radical, if you take the time to rewrite that radical in exponential form, then you can apply your power rule. So my derivative is going to be equal to that exponent times x to the 1 less power. So 1/2 minus 1 is going to be negative 1/2. When I go to simplify that, my derivative is going to be equal to 1 over 2 times the square root of x. The negative moves the exponent down to the denominator. And the 1/2 power means take the square root. If my x is in the denominator, I'm going to go ahead and write it in exponential form, because when I go to take the derivative, that negative 1 comes out in front. Then I have my x to the 1 less power. When I go to rewrite that, my negative 1 stays in the denominator or in the numerator, and my x moves down to the denominator with that negative exponent. Yeah.
Since we have the square root in the denominator, you can put get rid of it instead of this.
So that's a great question, because when you look here, you're like, wait a minute, can I just rationalize it and call that the square root of x over 2x? That is the more formal, simplified answer. Miss Holdaway and I agree. We're okay with you leaving it like this, so we can see that you understood the rule and can do it right. And there's going to be a lot of times when you're like, wait, do I need to simplify that? And I'm like, no, leave it the way it is so I can check and make sure that you did it right. When in doubt, ask. Okay. When you see 2 x's in the denominator, that means that you have x to a negative second power. So the derivative is going to be where your exponent comes out front times your variable to the 1 less power, and that's going to be negative 2 over x cubed. And you can see it fits the pattern where the slope of the tangent line is always going to be an equation that's 1 power level lower, 1 power level less. All right, what are you finding? What if you are finding the derivative of a constant multiple of the function? So if you're worried about what this means, the constant multiple of the function, here's our example here. For example, find the derivative of 5x squared. And what we want to do is use the limit definition of the derivative, and we can see what the heck are we supposed to do with this 5. So let's go ahead and say the limit as h approaches 0 of my function, my new function, minus my original, all over that h. So I'm going to have 5 times x squared plus 2xh plus h squared minus 5x squared all over h. So I'm going to have 5x squared plus 10xh plus 5h squared minus 5x squared all over h. Here's my 0 pair. And that's how I lose that power. I can always factor out an h, giving me 10x plus 5h. And that's going to be over h, and that's how I lose that h. Now my job is to plug in 0, because it's not going to give me an indeterminate form anymore. So I have 10x plus 5 times 0. So I end up with 10x as my derivative. Did you see how this 5 ended up being multiplied by each of those terms? This is the key here. And then ending up as that coefficient. So when I take this 2 out in front, if I have f of x equals 5x squared, when I bring this 2 out front, f prime is going to be 2 times that coefficient times x to the 1 less power. And that constant multiple is then going to be part of that coefficient. I crack up at this word, try, to find the derivative function of each function below without using the limits, using our power rule instead. So I'm going to pause the video, talk to your group mates, compare answers, and your mark it, set, go. All right, so now when we talk about the homework, we're back to this same idea of where x is and is not differentiable. And then on the back, you're asked to use the power rule. And then we gave you some practice of using the limit definition of derivative, so you're ready for today's quiz. So talk to your group mates, compare answers, you mark a set, go. All right, this is what we got for number 1. Come back and check your work with mine, please. Are we good? Give me a thumbs up. Okay, number 2. Are we good? So -2 is not 1. That's a smooth curve. So there's nothing wrong with the at x equals -2. All right, how about 3 and 4? Go ahead, Billy.
For the, I think you already said this, but for the not continuous, you have to put it in the not differentiable as well.
Yeah, no. So she put them in both here. I'm okay with, because I'm assuming that you know that if it's not continuous, it's not differentiable. All right. On the back, here's your power rule. 4 times 3 is 12. Take x down a power. 10 times 10 is -100. Take x down a power. 1 times -1/2 is -1/2. 3x squared is the derivative of x cubed. Here I take my power out to front as a coefficient and I subtract 2 over 2. -5 comes out as a coefficient. There's my 1 less. Down to the denominator it goes. The limit definition of a derivative ones, and this is where maybe as a mathy you completely geek out, but I love doing these and then going back and playing with the power rule and make sure that I verify that I did it right. Yeah.
Number 11, when you take the 2 things and make them the 2 square root, when you flip it, so then shouldn't it, because it's negative in the equation, shouldn't it be positive when you're doing the flipping thing?
So she has the original, Miss Holdaway did this key. So she has the original function, or the new function minus the original. And then it's interesting how she distributes her negative, crosses out her 4's before she does her conjugate. So see this here?
Yeah.
So she takes this minus, so it's 4 minus 4, and this minus turns this into plus. That's why her conjugate is plus, because that's plus. Yeah. So this negative out in front, this negative out in front is what the hang-up is. And that's why this has to be negative, because it's that minus that, and that's how we end up with that positive value. The work for 12 is fairly substantial. That's a lot of work. And then 13 is down here. That cube function, think about it. Yeah. Say that one more time. 13. All right, Nate, are you done with 12?
Just to cancel agents.
Are you okay? All right.
Miss Glazier,
Yes.
the quiz on quarter 1 or quarter 2?
Quarter 2.
Did I get a
The conjugate. So, what makes this one hard, Kiara? What makes this one hard? See if I can get it to stay. The wind's blowing now.
Okay, so yeah.
All right.
So
Oops. Boy, that's enough to make you seasick. Okay. So, Kara, what do you want to ask? Okay. So, because this is naturally set up as a negative, it's backwards, right? So, when she did this part of the function minus this, she distributed her negative and canceled these 4's out to combine like terms, right? And then, but this negative stood, and this negative carried out, making that positive. So she ended up with this negative plus this. So then when she did her conjugate, well, when she put 0 in for h, she ended up with this is my negative term and this is my positive term. So far, we've always had the positive minus to make. Positive minus the other one, right? But because this one is backwards, that's how we ended up with that. So our conjugate, if we have a sum, our conjugate's got to be the difference. So when I do the difference of two perfect squares, this is going to be this negative times a negative gives me a positive inside value. My middle two terms cancel out, my outside and inside terms. And then here's my positive times my negative, and that's what gives me this minus. When I distribute that negative, it becomes minus x minus 3, so that's how I get just h over top. When I stick 0 in for h here, I don't get, I think there should be a negative here. What do you think? Because it's negative minus another negative. It's my square root of x plus 3, right? I would put it, I think that this needs a negative in front. I think she dropped her negative here. Okay?
It's not okay.
That's the conjugate.
I think you should terminate the quiz. We have a democracy, but we're not here to do Can you what I'm on?
Yeah,
I understand 11. I understand 12.
Okay, can I see that after you? What?
So are we feeling okay?
Are you sure?
Are there retakes for this quiz?
Is it open note?
Hey, if you want to use your warm-up, use your warm-up.
Might not help. We kind of decided. I usually that I bring I cannot read the numbers.
You guys ready?
Well, I guess I'm ready.
Okay, so this little thing is distributed over here. You see it now? Yeah. I was like, damn. Thank you. Got it now, Chris?
Is everybody have paper? You have straight edges in your baskets if that helps you draw your tangent lines. Everybody loves a good tangent line.